that there is no rational number x such that x squared equals 2, that means we cannot write the number x such that x squared equals 2. We cannot write, nobody can write. But the thing is, there is a rational number x such that x squared equals 2. You can justify it from analysis, you can prove it. Also, you can prove it by Pythagorean theorem. If you take a right angle triangle with either side 1, then hypotenuse is x squared equals 2. No? Length of the hypotenuse, if you take x squared equals 1 squared plus 1 squared, which is 2. So, that way we know that there is a number whose squared is equal to 2, but nobody can write it. That's the funny thing. We only give a sketch of a proof. The proof I gave you is the shortest one. I mean, same thing can be written in a little shorter way if you know about greatest common divisor of numbers, integers. Suppose for the sake of contradiction that we had a rational number x for which x squared is equal to 2. We are going after a contradiction. We are assuming that there is a rational number x such that x squared equals 2. Clearly x is not 0, of course it goes without saying. We may assume that x is positive. If x were negative, then we would just replace x by minus x, since x squared is equal to minus x squared. So thus x is equal to p over q, like the way I wrote for some positive integers pq, such that p over q squared equals 2. Then we get p squared equals 2q squared. Define a natural number p to be even if p is equal to 2k for some natural number k, and odd if p is equal to 2k plus 1 for some natural number k that we know. Every natural number is either even or odd, but not both. I mean, it cannot be equals to 2k plus 1 and 2m. Then what will happen is, if 2k plus 1 is equal to 2m, then 2m minus 2k is equal to 1. So 2 times k minus m is equal to 1, never happens. No? Then 1 is an even number. You know? So every natural number is either even or odd, that is clear. If p is odd, then p squared is also odd. Asking why, I proved it, no? Over there, which contradicts p squared equals 2q squared. Thus p is even. Since p is even, p is equal to 2k, like the way I wrote for some natural number k. Since p is positive, k also must be positive. Inserting p is equal to 2k into that p squared equals 2k squared, we have 4k squared equals 2q squared, so q squared equals 2k squared. Actually now, p is even, q is even. I said I took p and q with no common factors, so that was a contradiction. He could have finished the proof here, but instead he is leading. To summarize, we started with the pair pq of positive integers such that p squared equals 2q squared, ended up with the pair qk of positive integers such that q squared equals 2k squared. Since p squared is equal to q squared, we have q is strictly less than p. He is asking why, I mean it goes without saying. If we write p equals q and q dash equals k, we thus can pass from one solution pq to the equation p squared equals q squared to a new equation p dash q dash to same equation which has a smaller value p. We started from p equals 2q. Then now we have q is less than p, q equals q squared equals 2k squared. So from pq we are going to q is smaller. Then he is saying if you write p dash is equal to q and q dash equals k, we thus can pass from one solution pq to equation p squared equals 2q squared. So we get another solution now. If we started from pq, now we have p dash q dash. Again p dash squared is equal to twice q dash squared. Understand, no? To the same equation which has a smaller value of p. But then we can repeat this process, he says. We can repeat this procedure again and again, obtaining a sequence p double dash q double dash. You understand, no? P triple dash q triple dash, etc. of solutions to p squared equals 2q squared. Each one with a smaller value of p. P is the biggest, then p dash, then p double dash, then p triple dash, and so on. It's going down. And each one consisting of positive integers. But this contradicts the principle of infinite descent. Let's go for that. I mean, that is clear, no? Without the proof. So, whatever you prove, if you think is true without the proof, that's very good. But he does is here, you have PQ. PQ couple, P squared is equal to 2Q squared. Then you go to P dash Q dash. Again P dash is equal to 2Q dash squared. Oh yes. Then he goes to P double dash, Q double dash, then P double dash is equal to 2Q double dash squared. The important thing, and this goes like without splitting soon. So this continues. So the thing is here, P is strictly greater than P dash, is strictly greater than P double dash, like this. And all these are positive integers. If you start from any positive integer p, you cannot do it forever. No? You cannot do it forever because all of them are positive. Even p is, for instance, 1000. If by any chance p is 1000, you can go at the most 1000 times. 999, 998, because p is the biggest, then p dash, p double dash, p triple dash. So that is called infinite descent. You cannot go forever. Actually, that's what. Let's go to that exercise also right away. Oh, it takes forever. Here, a sequence A0, A1 up to A of numbers, natural numbers, integers, rationals, whatever, is said to be in infinite descent if we have an strictly greater than an plus 1 for all natural numbers. A0, natural numbers n, it is strictly decreasing. Principle of infinite descent means prove the principle of infinite descent. It is an homework problem. That is, that it is not possible to have a sequence of natural numbers which is in infinite descent. I mean, it is obvious without a proof. Even if it's million, you can go up to only million terms. No, then you go to 0, then -1, -2, like that it goes down. It says prove the principle of infinite descent, that it is not possible to have a sequence of natural numbers which is in infinite descent. Proof is, you can say it goes without saying, but in maths you cannot write. Hint, assume for sake of contradiction that you can find a sequence of natural numbers. Anyway, it's a homework problem. No, I'm not going to do it now. If you cannot, you can do it. No big deal. But clear, no? I mean, you cannot, in other words, in our words, if you forget about the word infinite descent, what it says is, you cannot have a strictly infinite, strictly decreasing sequence of natural numbers. You cannot have. I mean, that is very clear. But this contradicts the principle of infinite descent. This contradiction shows that we could not have had a rational x for which x squared equals 2. Now anyway, I proved here, that is also clearer than this one. This one you have to do that homework problem. Again, that is also clear, because if you start from any positive integer, you can go only if it is 1000, you can go 1000 times below. I mean, if A0 is 1000, then A1000 will be 0. Thereafter you get negative numbers. This is also important one. On the other hand, we can get rational numbers which are arbitrarily close to square root of 2. That is important. Though there are no rational numbers, sorry, my English is incorrect. So though there is no rational number x such that x squared is equal to 2, what he says is that you can have rational numbers let's read this statement. For every rational number epsilon greater than 0, no matter which positive rational number you choose, actually sooner or later you don't need the rational number. For every real number epsilon greater than 0, there is a non-negative rational number x such that x squared is less than 2 is less than x plus x squared. What it says is that if you take the square root, though we cannot take x root 2, given any positive epsilon, now we don't know about real numbers, we know only about rational numbers as of now, given any real number x, positive epsilon, there is a rational number x such that root 2 is between x and x plus epsilon. Though there is no rational number x such that x squared is equal to 2, you can find rational numbers very close to the square root of 2. I mean, this is, you can put epsilon is equal to 10 to the billion minus billion. Then this is a rational number, x is a rational number in the number line, x, then x plus 10 to the minus billion is, you cannot draw, root 2 is in between. You can get, in other words, in our normal English, as close as you please, as much as you desire, to root 2 by rationals. There are rationals, in bad English, doesn't matter, damn close to root 2. As close as you want. So, it's an important thing. Of course, these will be trivial sooner or later. Now, what we are going to prove is that we know that there is no rational number for which there is no rational number x such that x squared equals 2. No matter how epsilon you choose, there is a rational x such that root 2 is between x and x plus that very, very small epsilon. So there are, I don't know how to say it, there are rational numbers as close as you desire to root 2. I mean, here he is not saying root 2 here because there is no such thing. But let's start. Proof. Let epsilon greater than 0 be rational. Suppose for sake of contradiction, there is no non-negative rational number x for which x squared less than 2 less than x plus 1 x plus epsilon squared. Assume that is not true. Prove by contradiction. This means that whenever x is non-negative and x squared less than 2, we must also have x plus epsilon squared is also 2. Why? When you assume, I should write. We are going to prove that there is no rational number x such that epsilon, for every epsilon he is assuming here, x plus epsilon squared. This is, suppose for sake of contradiction that there is no non-negative rational number x such for which x squared less than 2 less than x plus epsilon squared. What does this mean? If this is true, this cannot be true. So if x squared is less than 2, then 2 must be greater than or equal to x plus epsilon squared. Right? Now x is rational, epsilon is also rational. Then equal sign cannot happen. Because since x is rational, epsilon is rational, this thing is squared cannot be equal to 2, then this is what is going to happen. That is
X is rational.
Eh?
X is rational, then epsilon is rational.
Yeah. Doesn't he say like that? For every rational number, epsilon greater than 0. Epsilon is rational. Got it? So, what he is saying is, so if x squared less than 2, then, so okay, let me write it again. So, if x squared less than 2, then x plus epsilon also squared less than 2. Epsilon is given, by the way. Epsilon is a given one, it's not arbitrary. Arbitrarily fixed. If x squared less than 2, then x plus epsilon squared is also 2. Note that x plus, he says, x plus epsilon squared cannot be equal to 2 by proposition whatever, because x plus epsilon is rational, that is the reason. Now he says, now since 0 is squared less than 2, we know that no? We have epsilon squared less than 2. How do we know that? Since 0 is squared less than 2, over there what did we prove? You have to be careful. What we have proved was, if by any chance x is a rational number such that x plus x squared less than 2, then x plus epsilon squared also less than 2. Since 0 is a rational number such that 0 squared less than 2, then when you put x 0 in the place of x, you get epsilon squared less than 2, which is then 2 epsilon squared also 2. Why? If epsilon squared less than 2, now you put in the place of x, again epsilon. Epsilon plus epsilon squared less than, epsilon plus epsilon whole thing squared less than 2, that is 2 epsilon squared less than 2. And indeed a simple induction, you can prove it right away, n epsilon squared less than 2. For any n, that is going to be true by induction for every natural number n. Note that n epsilon is non-negative for every natural number n. I mean, it goes without saying. Epsilon is positive, n is an integer, n epsilon cannot be negative. Anyway, where am I? Yeah. By proposition 4.1, we can find an integer n such that, you said we did not do it. No, Archimedean property. What is Archimedean property? I guess. I don't know. Let me go to proposition 4.4.1. Did I say that name? Not the name is not there. Somehow it doesn't. I mean, it's a very important property, Archimedean property for analysis. Anyway, but this is on page 91. Archimedean property. It's not. I say Archimedean property. You don't know it. We have proved they are given any positive real number. You can find an integer n greater than that. That is proposition 4.4.1, which is on page 91. So by that proposition, you can find an integer n such that n greater than 2 or epsilon which implies that n epsilon greater than 2. You keep in mind that we can prove that given any real number there is an integer larger. We can prove it. I mean, we are using that here. N epsilon greater than 2. Then if n epsilon greater than 2, then you have n epsilon whole thing square must be greater than 2 square, which is equal to 4 greater than 2. Contradicting n epsilon square less than 2. For all natural numbers n, this contradiction gives the proof. So what we are proving here is a very important one. For any rational number epsilon greater than 0, there is a non-negative rational number x such that x square less than 2 less than x plus epsilon whole thing squared. Though there is no rational number whose square is 2, there are rational numbers very close to very close to, I mean, square root of 2. I mean, I cannot say it even without saying using square root of 2. Here he is saying, for example, here, did you get it, Putta? If epsilon is 0.001, he says then we can take x to be 1.414. Since x squared is, he says 1.39396 and x plus epsilon squared is 2.0032 and 5. So, I mean, it is that close. If you take x, when you take epsilon to be 0.001, you can do it anyway. We have proved it, no? We don't need even examples. Proposition 4.4.5 indicates that while the set cube of rationals does not actually have root 2 as a member, we can get as close as we wish to. Root 4, root 2. He is also writing root 2. We can get as close as we wish to root 2. For instance, these numbers are very close to root 2. So, that is a very interesting result, very important result, that there is no rational number whose square is root 2, but there are rational numbers as close as you please. As close as you please to the square root of 2. Very close. So, I mean, these real analysis type statements, thus it seems that we can create a sequence root of 2 by taking limit of a sequence of rationals. This is how we shall construct the real numbers in the next chapter. Real numbers are limit of sequence of rational numbers. We know we know natural numbers, then we learn about integers, then we learn about rational numbers. Now we are going to learn about sequences and something called Cauchy sequences. Limit of Cauchy sequences are the real numbers. They are real numbers. Now E, phi, nobody can write now. What is phi? I don't know. What is E? Nobody knows. What happens is this sequence 1 plus 1 over n raised to the power n. This sequence has a limit. Nobody knows what this limit is. Because you don't know it, you say it is E. You say it is E. That's all. Again, 1 plus 1 over 1 plus 1 over 2 plus 1 over 3 plus and so on plus 1 over n. We haven't done log still, but log en. This one has a limit. We don't know what it is. We call it gamma. We use some English letters or Greek letters to limit that. We don't know. 5, again 5 has so many interpretations. We don't know what it is, so you put 5 into the Greek letter. what happens is real numbers are limits of sequences. Limits, the sequences with limits are called Cauchy. Cauchy. C-A-U-C-H-Y. Cauchy sequences. I used to call it Cauchy. Cauchy. So they are very interesting things. So we are getting getting closer to very interesting stuff. But your homework is not graded yet. That's not a good thing. I don't have time. If I had time, I like to grade. But no, I cannot. I don't have time. Anyway, so this is how we shall construct the real numbers in the next chapter. There is another way to do so, using something called Dedekind cuts. That is very abstract. I haven't studied it yet. Yet means I will never study it over time. Which we will not pursue like here, which we will not pursue here. One can also proceed using infinite decimal expansions, that's what we know. But there are some sticky issues when doing so. Example, one has 0.9999, if you write without stopping, equals to 1.000 without stopping. So same number has two decimal expansions. So that's not a good thing. So as a result he says, and this approach, despite being the most familiar, that's the most familiar one, no? That's how we write real numbers, using decimals. I mean, that's the only way we know. Despite being the most familiar, is actually more complicated than other approaches. It's far more complicated. This defining the books, you have only the first two books, no? I myself have defined real numbers as limit of sequences, limit of rational sequences. So we construct integers, natural numbers, integers, rationals, then real numbers are limits of convergent sequences. They are the real numbers if somebody asks you. So we have to do that stuff, I guess, on the next lesson. Here he has this infinite descent thing. So that's, he has given, I guess, a hint. Of course, you can do without hint, but maybe you will. We justified the real numbers. Eventually we came to real numbers. The funny thing is that whatever we did so far and now going to do real numbers, the things we know about real numbers, we know about natural numbers, we know about integers, we know about rational numbers. Then to talk about the things we know, definitions, how it was constructed, is kind of not that friendly, because sometimes when I was in the first year of Colombo University, I was given a homework problem, tutorial problem to prove 1 greater than 0. I was very mad, Jacob, what to prove? Everybody knows 1 greater than 0. But it is a good problem. Anyway, so you have any questions about what we discussed so far? Anyone has any questions? Because these natural numbers were constructed using Peano axioms, which included by the principle of mathematical induction. Then he came to construct the integers. Then came to rational numbers. No, integers, yes. Integers were, defined by difference of natural numbers, a long dash b. Then he came to rationals, p over q double dash. And now real numbers. Again, in real numbers he is using something little funny. He is doing it. So after this chapter, constructions are over. Then we are going to study analysis. I think it is very good to finish the homework before we do chapter 6, but you don't have a grade, you know. How should it be done? I don't know. I will talk to him. Without grading homework, you have to receive the graded homework with comments. This is not true, this cannot, because it is very important, especially because you are introduced natural numbers, integers, rational numbers, etc. You are introduced. Okay, so let's start see how we see. But remember, natural numbers were constructed by Peano axioms. First one was the principle of mathematical induction. Actually, in my book, I didn't have the book, I have proved the principle of mathematical induction in 2 ways. But to him it is an axiom. Axiom. So once you understand some maths, my book is very good for you to read. Anyway, the thing I told you, this it is incompleteness axiom is a very famous one. Every non-empty subset of R which is bounded above has a least upper bound in R. It is an axiom. It is called completeness axiom. But he is proving it. I don't know. Let's go. The real numbers. So I am going to assume that you know about natural numbers, integers and rationals. Now, the real numbers. Anyone has anything you want to, do you have any question about, not how to solve the problem, but about the constructions or something bothering you? Do you have anything which bothers you about?
The power zero thing bothers me.
Yeah, I'm in the same boat with you.
Other than that, not much from after I done the homework, probably I'll get some.
Yeah, you need to do the homework, but it must be read. I'm going to call him. I will say, forget about your lunch. No, actually, after all, that's how you learn. You learn because the person who grades must have to have a very good knowledge about this. Not everybody can grade this. Yeah, even my logic problems, though they are simple, not everybody can grade. Can you see here? This book has logic errors, no? Even though he is almost the best in mathematics in the world. Okay, let's go. We can do something now, we have some time here. To review our progress to date, we have rigorously constructed 3 fundamental number systems: the natural number system N, the integers Z, and the rationals Q. We defined the natural numbers using the Peano axioms and postulated that such a number system existed. He said it is an axiom, no? This is plausible since the natural numbers correspond to the very intuitive and fundamental notion of sequential counting. This is sort of this natural, no? You 1, 2, 3, 4. Without rigorous Peano axioms, you count, you know about it. Yeah, no Peano axioms. Using the number system, one could then recursively define addition and multiplication and verify that they obeyed the usual laws of algebra. Again, what you know. We then constructed the integers by taking formal differences of the natural numbers a ln dash b. We then constructed the rational numbers by taking formal quotients of the integers a double dash b, although we need to exclude division by 0 in order to keep the laws of algebra reasonable. You are of course free to design your own number system, possibly including one where division by 0 is permitted, but you will have to give up one or more of the field axioms from proposition 4.2.4 among other things, and you will probably get a less useful number system in which to do any real world problems. You are not going to define it, so I just read it. Because if somebody comes up with something new, which includes division by 0, then it is a useless one. Actually, I am very unhappy. He says 0 to the 0 is 1. In my books, I have written explaining it is not defined this and that. It is an indeterminate, that's the term. Indeterminate, cannot determine. Anyway, the rational system is already sufficient to do a lot of mathematics. Much of high school algebra, for instance, works just fine if one only knows about the rationals. However, there is a fundamental area of mathematics where the rational number system does not suffice that of geometry, the study of length, areas, etc. For instance, a right angle triangle with both sides equal to 1 gives the hypotenuse of root 2, which is an irrational number. That is not a rational number. Did he give the meaning of irrational number? He did not give. So, actually, some people are very unhappy about the fact that irrational numbers are given irrational number. Name irrational because this number, you cannot prove it today, but someday I will design as a homework problem. But before that, who can grade the homework? I will insist Prabhat. He should grade. Otherwise, your progress will be very slow. Now this number 0.1, 0, 1, 0, 0, 1, 0, 0, 0, 1. Can you see? It's nice number. This is very rational. No? You know the English meaning of rational? People those who are doing politics are irrational. Right? I don't think they know the meaning of rational. I don't want to tell the names because this is going to be taped. 1, 0, 1, 0, 0, 1, 3 zeros and 1, 4 zeros and 1. Like that, if you continue like this, you get a nice, this is very nice. But this is an irrational number. You can prove it. If one other important thing, now you are taking this class, if you ask somebody who has not studied my books, give me an example of a rational number, I will take a bet. Nobody can give. Even you couldn't have given if I had asked you before I give you this. Do you know any rational number? Means you know any, can you write an irrational number? Oh, nobody can. No, I shouldn't say nobody can. If you know this one, for instance, this is an irrational number. You can prove it, but not now. You can prove it. So the reason many mathematicians didn't like or don't like the fact that this is an irrational number, because this is it has a very, you can tell every decimal point. It's a very nice, there is a good pattern, but still it is irrational. So people are very unhappy to say that this is an irrational number. But it is irrational. Anyway, somebody asks you, give an example of an irrational number. Keep in mind, this is irrational. If you are asked to prove, give me a range check, you say that. You want to go slow. So, although there are so many irrational numbers, majority of the real numbers are irrational. But people usually don't know. If you go and ask an engineering faculty professor or student or anybody, give an example of an irrational number? They cannot give. I mean, in the sense, can you write an decimal expansion? No. They don't know. I mean, for instance, root 2, nobody can write. No? 5, nobody can write. E, nobody can write. But the funny thing is, almost all the real numbers are irrational. But we cannot write an irrational number. Decimal expansion we cannot write. Okay, let's go. Where was I? Root 2, which is an irrational number, that is not a rational number. See, things get even worse when one starts to deal with the subfield of geometry known as trigonometry. When one sees numbers such as 5, cos 1 is an irrational number, 5 is irrational, which turn out to be in some sense even more irrational than root 2. These numbers are known as transcendental numbers. Transcendental numbers, Sinhala word is Lokottara. Lokottara Sankhya. So, something like, again, because I told you that word, to make you educated, root 2 is a solution of this equation. Numbers which are roots of polynomial equations are called algebraic numbers. Algebraic. ALGEBRAIC. Algebraic numbers. Root 2 over root 3 plus 1. This is an algebraic number. All of you can write a polynomial such that this is a root of it. Very easy to write. They are called algebraic numbers. And real numbers which are not algebraic, now root 2 is algebraic, though it is irrational. It is a solution of this equation. Real numbers which are not algebraic are called transcendental numbers. Most of the real numbers are transcendental. Can anyone write a transcendental number? They are very big problems. Very big problems. Do I know that whether this number is transcendental or not? I don't. I haven't tried to tell you the truth. I think this is transcendental, but I cannot say. You understand? Root 3, these kind of numbers they are roots of some polynomials. When I say polynomial, these coefficients are rational numbers. One can say this is also a polynomial, no? But this is not a rational number. When I say polynomial, I am talking polynomials with rational coefficients. Some number is said to be algebraic if it is a solution of a polynomial with rational coefficients. Polynomial equation. So E and phi they are algebraic, not algebraic, they are transcendental. So they are called, did he write here transcendental? Yes. These numbers are known as transcendental numbers. But to discuss this further would be far beyond the scope of this text, of course. Thus, in order to have a number system which can adequately describe geometry, or even something as simple as measuring lengths on line, one needs to replace the rational number system with the real number system. The number world is so complicated. Since differential and integral calculus is also intimately tied up with geometry. Think of slopes and tangents or areas under a curve. Calculus also requires the real number system in order to function properly, and he is justifying the reasons. However, rigorous way to construct the reals from the rationals turns out to be somewhat difficult, requiring a bit more machinery than what was needed to pass from the naturals to the integers or the integers to rationals. It is more than that. It was easy to pass from naturals to integers by taking lone dash, no? Then from integers to rationals, it was easy by taking this double dash method. Real numbers, you cannot go that way. I mean, if you are given two, I mean, the way we constructed rational numbers, it was very easy, no? I mean, you took the intuition, but here there is no such thing. However, rigorous way to construct the real is out to be somewhat difficult, requiring a bit more machinery than what was needed to pass from rationals to integers or the integers to the rationals. In those two constructions, the task was to introduce one more algebraic operation to the number system. Example, one can get integers from naturals by introducing subtraction and get the rationals from the integers by introducing division. But to get the reals from the rationals to pass from a discrete system to continuous one and requires the introduction of somewhat different notion, that of a limit. We need that. So it is far more complicated than going from naturals to integers or integers to rationals. It is a very big step. The limit is a concept which on one level is quite intuitive. But to pin down limit, when you talk about it, it is very intuitive. But to really pin down what it is a difficult thing. Most of the people don't understand the meaning of limit. That's why they say mathematics is difficult. That's the reason. This is a concept which on level is quite, on one level is quite intuitive, but to pin down rigorously turns out to be quite difficult. Even such great mathematicians as Euler and Newton had difficulty with this concept. It was only in the 19th century that mathematicians such as Cauchy and Dedekind, he mentioned about Dedekind cuts before, figured out how to deal with limits rigorously. So, in other words, we are going to define, as I told you, real numbers using the word limit. So far we don't know what limit is. Limit is also, but funny thing is you know the meaning of limit. No, I mean you feel limit of 1 over n as n tends to infinity is 0. Limit of n plus 1 over 2n plus 3 as n tends to infinity is n plus 1 divided by 2n plus 3. N plus 1 divided by 2n plus 3. Limit of this thing is limit of 1 over n, you said it is 0. Limit of this one is 1 over 2. You did not do much limits in error?
No, we did. That's why I told you half you did. I told half first.
Did you say?
Yeah.
Sorry, I didn't hear. Sorry. So, now you don't know what limit is. You know the limit of 1 over n is 0. You don't know. You know the limit of n plus 1 over 2n plus 1 is 1/2. Like that you know. But if somebody asks you, what is the meaning of limit? You don't know. So, it is complicated thing. Very many interesting, jolly exercises related to limits. So, where am I?
Section 4.4.
In section 4.4, we explored the gaps in the rational numbers Now we shall fill in these gaps. Actually, that's what we are doing. Because we can prove that between any two rational numbers, regardless of how close they are, there are infinitely many rational numbers. So many, much more than rational numbers. Gaps, in section we explored gaps in the rational numbers. Now we shall fill these gaps, fill in these gaps using limits to create real numbers. The real number system will end up being a lot like the rational numbers, but will have some new operations, notably that of supremum, which can then be used to define limits and hence to everything else that calculus needs. We are going to learn the word supremum. Supremum, there is another word, infimum. It's not, he didn't say it here. So, when it comes to rational numbers, you don't get this sort of word. So, but with the real numbers, supremum is a very, very important word. The procedure we give here of obtaining the reals, I am reading everything because it is very important. The procedure we give here of obtaining the real numbers as the limit of sequences of rational numbers may seem rather complicated. So real numbers are limits of sequences with rational numbers. It looks complicated because we cannot imagine. However, it is in fact an instance of a very general and useful procedure, that of completing one metric space to form another. He used the word metric space here. Have you? Yeah, that's the thing. You don't know what metric spaces are. He knows it. So that's the thing, I think, some weakness in this book. Cauchy sequences, very, very important word, Cauchy sequences. So from today onwards till you die, you have to live with Cauchy sequences, especially you. You are going to be a mathematician. They are interesting. Our construction of the real number shall rely on the concept of a Cauchy sequence. Cauchy. Before we define this notion formally, let us first define the concept of a sequence. Actually, you know the meaning of a sequence. Again, he is making it difficult. Sequences, let M be an integer. A sequence an going from m to infinity of rational numbers is any function from the set of all n belongs to Z such that n greater than or equal to Q. He is talking about, usually, I don't know, he is making it difficult. You have this set m plus 1, m plus 2, this kind of sequence to Q. You consider sequence. That's right. When he says n going from m to Q, so sequence is, then he has am plus 1, am plus 2, like that sequence of rational numbers is any function of the set to Q. That is a mapping which assigns to each integer n greater than or equal to m a rational number a. More informally, a sequence n going from m to infinity of rational numbers is a collection of rationals m plus 1, m plus 2, and so on. That sequence, that is the meaning of a sequence according to him. But usually when others write, sequence is a function from set 1, 2, 3, 4, Z plus according to you to real numbers. Oh, but wherever it is. Now he is beginning from, not from 1, but from m. Can you see? So any sequence is any collection of rational numbers. am plus 1, am plus 2. I mean, you can give this, for example, you say am. You say an is 1 over n. You say an is n squared divided by 3n plus 1. These are sequences. Maybe beginning from m. am is 1 over m, am plus 1 is 1 over m plus 1. Like that. Yeah, that's all. No big deal. So sequences. According to him, in his case, domain is of the sequences m plus 1, m plus 2, m plus 3 and so on. Range is q and the function is, he is writing in the form am plus 1, am plus 2. That is very standard. Here he is writing an example. Example 5.1, the sequence n squared is 0, 1, 4, 9 of natural numbers. Is beginning from 0. That is the sequence. Then the sequence 3 continuously, constant sequence, that is the sequence. The sequences are indexed starting from 0, but we can of course make sequences starting from 1 or any other number. You can start from anywhere. In his definition, he started from m. Then the first example, n squared, he began from 0. Constant sequence, he began from 0. You can start from anywhere. I mean, when you say starting from m can be any number. For instance, the sequence n going 3 to infinity denotes the sequence a3, a4, a5, like that. So n squared, n going 3 to infinity is 9, 16, 25, like that, of natural numbers. We want to define the real numbers as the limit of sequences of rational numbers. That's what we want to do now. So far we discussed about the sequences. So sequence for us is a function from m plus 1, m plus 2, m plus 3 and so on for some m to q, which can be written as am plus 1, am plus 2, am plus 3, and it is a formula like here 1 over n squared or constant 3. We want to define the real numbers as the limits of sequences of rational numbers. To do so, we have to distinguish which sequence of rationals are convergent. You don't know the meaning of convergent, but he says that, and which ones are not. For instance, the sequence 1.4, 1.41, 1.414, 1.41, 4142, 1.41421 looks like it is trying to converge to something, as does 0.1, 0.01, 0.001. It appears that they are trying to get converged to something. However, 1, 2, 4, 8, 16 doesn't approach anything, no? It gets bigger and bigger. 1, 0, 1, 0, 1, 0 doesn't get close to anything. It is jumping from that side to this side, like jumping from 1 to 0, like Sri Lankan politicians, no? So not getting close to. So he's anything, no? Not getting close. To this, we use the definition of epsilon closeness defined earlier. Recall from definition 4.3.4 that two rationals xy are epsilon close if dxy is mod of x minus y less than or equal to epsilon. So now you don't know the meaning of convergent sequences, but you have sort of a feeling. Now when you say 1.4, 1.41, 1.414, maybe this is getting closer to something. You are getting the feeling. May not be. I mean, rigorously may not be, but intuitively you feel. But 1, 2, 4, 8, 16, it doesn't get close to anything. And 1, 0, 1, 0, 1, 0, 1, 0, like our politicians, they don't get close to anything. They get close to where there is money. Okay, so let's see definition. Epsilon is steadiness. remember, this is not real analysis, he is trying to define real numbers using rational sequences. That's what he is on the way. Let epsilon greater than 0. A sequence n going 0 to infinity is said to be epsilon steady. If and only if each pair aj, ak of sequence elements is epsilon close for every natural number jk. You have a sequence an that begins from 0. You have a0, a1, a2, a3, a4 like that. You say that this is epsilon steady. That's his word. If and only if, no matter what pair you choose aj and ak from the sequence elements, epsilon goes for every natural number jk. In other words, the sequence a0, a1, a2 is epsilon steady. If and only if d, a, j, a, k less than or equal to epsilon for all j, k. You have a sequence a0, you have the sequence a0, a1, a2, a3, a100, a1000. Like this you have. This is epsilon steady means we say the sequence is epsilon is said to be epsilon steady. You take any two terms from this sequence. Any two. Say suppose you take A3 and A1000. This is less than or equal to epsilon. Any two terms less than or equal to epsilon, then he calls it is epsilon is steady. That is his definition. Now he has a remark here. This definition is not standard in the literature. You will never see this definition in any other book. We will not need it outside of this section. Even this book, we don't need it after this lesson. Similarly, for the concept of eventual epsilon steadiness below, we are going to say eventually steady after a while. That's what he is saying below. We have defined epsilon steadiness for sequences whose index starts at 0. So he said it is beginning from 0, no, in the definition. We have defined epsilon for sequences whose index starts at 0, but clearly we can make a similar notion for sequences whose indices starts from any other number. A sequence a plus 1 is epsilon steady. You can talk like that also. You don't have to start it from 0. You can go somewhere beyond. That's why he says a sequence a plus 1 is epsilon steady if one has daj ak less than or equal to epsilon for all jk greater than or equal to n. Over there he began it from 0. He says you can begin from anywhere onwards. Now he says saying this sequence 1 0 1 0 whatever it is, 1 is steady. Distance between any two terms is at the most 1. But it's not 1/2 steady. I mean, if you take the first one and the second one, distance is 1. 1 is not less than 1/2. No? Therefore, it's not 1/2 steady. You understand? The sequence next one, 0.1, 0.1, 0.01 is 0.1 steady. Why? If you subtract 0.1 minus 0.01, something less than 0.1. No? Therefore, it is 0.1 steady, but it's not 0.01 steady because difference between first two is not less than 0.01. The sequence 1 to 4 is 16 is not epsilon steady for any epsilon. Why? Because if you are given epsilon, far away terms are, first term, and if you take the 100th term, first term and 100th term here is 2 to the 100, no, I don't know what it is by the way. 2 to the 100 is the humongous number. No, that is very clear, no? 2 to the 100 minus 1 is a humongous number, it will not be less than epsilon. So that sequence is not epsilon is ready for any epsilon. The sequence 2 to 2 to 2 is epsilon is ready for any epsilon. Why? Difference between any two terms is 0. So it is for any epsilon. The notion of epsilon necessariness of a sequence is simple, but does not really capture the limiting behavior of a sequence, because it is too sensitive to the initial numbers of the sequence. Because when you talk about sequence, limit of a sequence, beginning terms, they are redundant initial terms. Limit is what happens far away, far at the end, not at the beginning. Not at the beginning. It has nothing to do with. Suppose a sequence, you have a sequence, let me ask you. First term is 1, second term is 1, third term is 1, 100th term is 1, 1000th term is 1, million term is 1, billion term is 1. What do you think of the limit of the sequence? What do you think? Buddha? Buddha? Naturally you think it is 1 because I said first term is 1. Then I said you go there, 10th term is 1. This is 10th term. Then I said you go to the 100th place, it is 1. 100th place. Then I said you go to the million place, again 1. 10 to the 6 or 5, I cannot remember. You go to the billion place, again 1. So, continuously 1. So one tend to think the limit is 1. That is normal human thinking. Continuously 1. So limit must be 1. But what happens? Look at this equation. Say n is 1 between n and 10, I don't know, 10 to the power billion. Suppose 0 after that. What is the limit of this sequence? Limit is 0. So what happens at the beginning is redundant. It doesn't play any role at all as far as the limit is concerned. But average human being, say, you go and say somebody, okay, limit, first term is 1, 10th term is 1, 100th term is 1, million term is 1, billion to the billion term is 1. What do you think of this? Oh, it must be 1. But limit is something which forgets about the origin, like Sri Lankans. We forget about, who helped us, who, did this and that to us. That's the way Sri Lankans are. Because it is too sensitive to the initial numbers of the sequence. For instance, the sequence 10, 0, 0, 0 is 10. 10 is steady, but it's not epsilon is steady for any smaller value of epsilon, despite the sequence converging almost immediately to 0. First term is 10, all the other terms are 0. So, limit is obviously 0. So, birthplace is not important for the limit. What happens at the far away, at the end, matters for the limit. So we need a more robust notion of steadiness that does not care about the initial members of a sequence. Remember, initial members don't play any role whatsoever as far as the limit is concerned. Nothing to do with the, here for instance, the sequence, this is a very important one. You will get this in your analysis problems sooner or later. Definition: eventual epsilon steadiness. Let epsilon greater than 0. Eventual antima kaledi epsilon steady. I have to go to single word anyway. Let epsilon greater than 0. The sequence n going 0 to infinity is said to be eventually epsilon steady. Finally epsilon is steady. At the end epsilon is steady if and only if the sequence capital A n plus 1, A n plus 2 is epsilon is steady for some natural number n greater than or equal to 0. After some n, it is going to be epsilon is steady. In other words, the sequence A0, A1, A2 and so on is eventually epsilon is steady if and only if there exists an n greater than 0 such that dAj, ak less than or equal to epsilon for all jk greater than or equal to n. It doesn't matter what happens for the initial terms. What matters is what happens after some natural number n. That's what it says. So that's a very important thing. So these are, you are learning little analysis things now. The sequence A1, A2 defined by an is equal to 1 over n. That is the sequence 1, 1 half, 1 third, 1 fourth and so on. It's not 0.1 steady, but it's eventually 0.1 steady because the sequence A10, A11, A12, it is A1 over 10, 1 over 11, 1 over 10 is 0.1 steady, no? Because the first term is 0.1. The sequence 10, 0, 0 is not epsilon steady for any epsilon less than 10, but is eventually epsilon steady for every epsilon greater than 0. Can you see that? Because if you begin from 2, after 2 difference between any two terms is 0. So it is less than any epsilon. So when it comes to limit, remember our initial terms do not play any role whatsoever. Now we can finally define the correct notion of what it means for a sequence of rationals to want to converge. So far we don't know the meaning of converge, but he wants to define the correct notion of what it means for a sequence of rationals to want to converge. Cauchy sequences, that's the term. A sequence A n going 0 to infinity of rational numbers is said to be a Cauchy sequence if and only if for every rational number epsilon greater than 0, the sequence A n going 0 to infinity is eventually epsilon steady. That's the meaning of Cauchy. Cauchy means eventually epsilon is steady. That means after somewhere after some capital N, if you subtract any two terms and get the absolute value, it is less than or equal to epsilon. That's what it means. In other words, the sequence A0, A1, A2 and so on is a Cauchy sequence if and only if for every epsilon greater than 0, there exists an integer n greater than or equal to 0 such that dAj, ak less than or equal to epsilon for all jk less than greater than or equal to n. Now this is the meaning of Cauchy. Now, Puta, can you tell me a sequence xj, xn? Because I am looking at the watch. Today is a sort of rainy day, so I don't know how the traffic will be. This morning we had hard time. So I have the sequence A0, A1, A2, A3, bingo, bingo, forever. You know, this is Cauchy, if and only if for each epsilon greater than this one. For each epsilon greater than 0, there exist. Is that how we wrote? Yeah, we have it that way. There exists an integer. This is an integer natural number. There exists a, no, come on, now let me write this. There exists an integer n such that d, a, j, a, k less than or equal to epsilon for each j, k greater than or equal to n. Because not every sequence is Cauchy. You know, there are some sequences which are not Cauchy. Buddha, can you tell me what is the meaning of is not Cauchy? A0, A1, A2, bingo, bingo, is not Cauchy if and only if what? If it is Cauchy, there is an epsilon greater than 0. For each epsilon greater than 0, there exists an integer n such that daj, ak less than or equal to epsilon for each ak greater than or equal to n. If it is not Cauchy, because certain sequences are Cauchy, certain of them are not Cauchy. So we need, sometimes we get to prove sequence an is Cauchy. Sometimes we have to prove it is not Cauchy. So in order to prove that sequence is not Cauchy, we have to know the meaning of not Cauchy. What is the meaning of not Cauchy, Buddha? We have the meaning of Cauchy on the board. Next, Buddha.
If it is not Cauchy, then there can exist in that fulfills that condition.
No, I'm asking me something I can write on the board without views. Buddha, very good. There exists
Epsilon
there exists epsilon greater than 0.
such that
Excellent. Very good. For each, no? Integer n. Very good so far. You are doing very well. For each integer n, comma, excellent. Very good.
distance of A, J, and AK
Distance aj, ak
is greater than epsilon greater than epsilon for some
Appa. If I had money, I would have got lunch for you today. Excellent. This is what you wanted to say, right? Exactly the negation. If it is, this is not Cauchy, how? There is at least one epsilon positive. How? No matter which integer you choose, n. If it is Cauchy, now you have terms now. Here is A0, here is A1, here is A2, like this. I just write like this. If it is Cauchy, no matter which epsilon you choose, there is an integer n. After that, distance between any two terms is at the most epsilon. Not Cauchy means there is at least one epsilon positive. How? No matter which n you choose, you can choose at least one AJ and AK. Distance between AJ and AK greater than epsilon, but this J and K is greater than n. Very important. If you got this one correct. If you cannot get it, you are not doing it. Very good, very good. So, if you want to prove epsilon a sequence is Cauchy, you have to begin let epsilon greater than 0. That's the starting statement. If you want to prove it is not Cauchy, you want to say let epsilon equals some number, 1 or 1/2 or something. Then you have to say no matter which integer you choose n, you can find two integers greater than capital N such that the distance between these two terms is greater than epsilon. Some people still cannot write the negation. That's not good. That's not good. No. Because after chapter 6, every day we are not talking about piano axioms. No, they will be history. We are going to do analysis, so you must be an expert in this. Because he gives the meaning of Cauchy. Indirectly he is giving the meaning of not Cauchy also. We have to be able to write negation of not only that, eventually Cauchy, bounded, unbounded. He gives the definition of bounded, then we have to know the definition of unbounded. That's the negation of it. All right. So I wish I had time to continue because it's a bit interesting. Anyway, after chapter 6, it will be more and more interesting day by day.